It would be difficult to visit Boulder and not be struck by the rock formations that shoot up to the west of town, forming a majestic backdrop that is unmistakable even from a distance. These impressive rock slabs were nicknamed the Flatirons by early settlers because their shape looked like an old-fashioned iron. Traditionally in geology, a flatiron is defined as a steeply sloping triangular landform created by differential erosion. As noted in some, but not all definitions, a number of flatirons are perched upon the slope of a larger mountain, with the rock layer forming the flatiron inclined at the same direction as, but often at a steeper angle than the associated mountain slope, such as the ones we see right behind me. Whether you're a technical climber or simply enjoying the views, the area provides an array of spectacular rock formations. It is hard to imagine Boulder without its iconic backdrop, but the rocks that you see have a long and varied history. How do we know this? The answer lies in the rocks themselves. Once you take the time to examine them, you can discover the clues that they reveal. There were 3 distinct stages that led to the formation of the Flatirons. The first stage of construction was the deposition of a thick layer of sand and gravel which occurred about 300 million years ago when the ancestral Rockies were completely eroded. Powerful rivers draining these ancestral peaks carried sand and gravel to the adjacent plains, where they accumulated in a massive 1,000-foot thick sediment that geologists have named the Fountain Formation. The ancestral Rockies were eventually worn down completely, and the eroded material formed younger sedimentary rock layers on top of the buried Fountain Formation. Even our Flatirons are made from recycled materials. The next stage of the Flatirons construction is the result of a unique event that occurred 70 to 80 million years ago, known as the Laramide orogeny. This orogeny caused a renewed period of uplift and deformation from Canada all the way to northern Mexico. The easternmost extent of this mountain building is represented by the Black Hills of South Dakota. This type of event is usually associated with the subduction of one continental tectonic plate under another. The subducted plate melts into a hot layer of viscous molten rock deep under the Earth's crust. In this instance, the subduction zone is off the coast of California, where it causes faults like the San Andreas, as well as earthquakes, volcanoes, and the Sierra Nevada mountains. This event also uplifted the modern-day Rocky Mountains and the western Great Plains. But how could this event have affected Boulder, which is 600 miles east of the Pacific Ocean? Geologists speculate that a particularly low-angled subduction of one tectonic plate beneath the other caused mountainous bulges to deepen the North American continent. These forces pushed up the Flatirons and its neighboring mountains. The subducted plate, known as the Farallon Plate, took an unusually shallow angle under the North American plate. The Farallon Plate did not descend into the Earth's mantle until it moved east, causing the upheaval of the Colorado Plateau. The third and final event that made the Boulder Flatirons so unique is the cement that hardened them. Although the foundation formation stretches the length of the Front Range, Boulder is unique because of its dozens of well-formed flatirons. This is due to a geologic quirk. Here, and only here, the fountain's layers are held together by an unusually strong cement called aldura, which is called moonstone when it's gem quality. This cement formed only in Boulder because on 2 occasions, about 135 million and 94 million years ago, warm potassium-enriched water welled up along an ancient fault zone that stretches between El Dorado Springs and Idaho Springs. The fountain formation's grains reacted with that water to form the aldura that tightly cemented its grains together and ultimately gave us these impressive rock slabs today. Rocks are indeed good storytellers, and the Boulder geologic story is still in the making. We live on a restless, dynamic planet, and we can be certain that geologic processes and landscapes will continue to change.